October 13th, 1942. Espiritu Santo, New Hebrides. Lieutenant Commander James Walsh crouches in a coral trench as Japanese bombers scream overhead at treetop level, their payload detonating across the newly constructed airfield with enough force to throw men 30 feet through the air. The temporary above-ground structures that housed aviation fuel, ammunition, and wounded Marines disintegrate in seconds. 7 sailors die instantly. 14 more suffer wounds from flying coral fragments that slice through flesh like razors. In the smoldering aftermath, Walsh surveys the devastation and realizes the terrible truth his superiors back in Pearl Harbor haven't yet grasped. Building on the surface in the Pacific Theater is a death sentence. Within 72 hours, Walsh drafts an urgent report that will fundamentally transform American military construction doctrine across every Pacific island from Guadalcanal to Okinawa. The message is brutally simple: go underground or die trying. What follows is an engineering revolution fought with dynamite, coral, and desperate ingenuity. American construction battalions learning to burrow into volcanic rock and island substrata, while Japanese bombers hunt them from above, creating subterranean fortresses that could withstand 500-pound bombs, Category 5 Typhoons, and tropical heat that liquefied conventional building materials. The race isn't just against the enemy. It's against geology, climate, and the calendar itself, because the invasion of the Gilberts is scheduled for November 1943, and every base between here and Tokyo needs to be bomb-proof before then. The problem facing American military planners in late 1942 is unprecedented in warfare history. Traditional fortification doctrine, developed over centuries in temperate climates, assumes you can pour concrete foundations, build thick masonry walls, and trust your structures will stand for decades. But the Pacific destroys these assumptions within weeks. The coral atolls where American forces must establish forward bases offer no bedrock for foundations, no native stone for construction, and no high ground for defensive positions. The volcanic islands provide rock for tunneling, but the basalt is so dense that standard drilling equipment breaks within hours. The tropical climate adds another layer of hell. Humidity, above 85% year-round, causes steel to rust through in 8 months, concrete to crack from thermal expansion within a year, and any organic material to rot or be consumed by insects within weeks. Then there's the enemy. Japanese bombers operating from Rabaul can hit targets 700 miles away. Their pilots, many of them veterans of campaigns in China and Southeast Asia, have learned to attack at dawn when defenders are least alert, coming in at wave-top height to avoid radar detection, then pulling up just seconds before releasing their payloads. A single bombing run can crater an airfield, destroy fuel depots, and kill dozens of men. The mathematics are devastating. It costs the Japanese approximately $800 in fuel and ordnance to conduct a raid that destroys facilities worth hundreds of thousands of dollars and kills irreplaceable trained personnel. American commanders calculate that without hardened shelters and underground facilities, their casualties from bombing will exceed their combat losses in ground operations. The solution begins with coral. Specifically, the fossilized limestone structures that form the geological skeleton of Pacific atolls. Navy engineers discover that mature coral, properly excavated and compacted, can be cut and shaped almost like soft stone. More importantly, coral that's been dead for thousands of years has compressive strength approaching 4,500 pounds per square inch, comparable to commercial-grade concrete. The breakthrough comes when construction battalion engineers at Funafuti realize they can excavate coral using the same techniques miners use for soft rock. Drill a pattern of holes, pack them with dynamite, detonate in sequence, then remove the fractured material with hand tools and small tractors. The resulting excavations can be roofed with salvaged steel, covered with 3 to 6 feet of coral fill, and camouflaged with native vegetation to create bomb shelters that are virtually invisible from the air and capable of surviving near-miss explosions. But theory and practice diverge violently when you're working under combat conditions. The first large-scale underground construction project begins at Espiritu Santo in November 1942, when the 7th Construction Battalion receives orders to protect the island's aviation fuel supply. The specifications sound straightforward. Excavate storage chambers for 12 1,000-barrel tanks, each tank requiring a cavity 40 feet in diameter and 60 feet deep, connected by access tunnels to a camouflaged pumping station on the shore. Total excavation volume, approximately 120,000 cubic feet of solid coral and basalt. Timeline, 60 days. Available equipment, 6 jackhammers, 4 air compressors that break down constantly in the humidity, 2 tons of commercial dynamite, and 500 men who've never worked underground in their lives. Chief Construction Electrician Thomas Rigger, a former Pennsylvania coal miner, takes charge of the excavation crews. His first lesson is harsh. Pacific coral isn't uniform. Near the surface, it's porous and relatively soft, but 20 feet down it transitions to dense basalt that dulls drill bits within minutes and requires 3 times the explosive charge to fracture. The air compressors, designed for sea-level operation, lose 30% of their power in the tropical heat. The jackhammers vibrate so violently in the dense rock that operators can only work 20-minute shifts before their hands go numb. Rigger adapts mining techniques he learned in Appalachian coal seams, establishing a rotation system where crews work in pairs. One man operates the hammer while his partner provides water to cool the bit and clear rock dust from the hole. Every 4 hours, the crews rotate out completely to recover. The dynamite presents its own challenges. Commercial explosives designed for American climates become unstable in 95-degree heat with 90% humidity. The gelatin-based compounds start to sweat nitroglycerin within 48 hours of removal from refrigerated storage. 2 men from Company C die on November 19th when a case of dynamite they're carrying detonates spontaneously. The investigation reveals the explosives had been stored in a surface magazine where internal temperatures exceeded 110 degrees. Rigger immediately orders the construction of an underground explosives bunker, excavated 15 feet into a hillside and roofed with double layers of corrugated steel separated by 2 feet of coral fill. The internal temperature stays 20 degrees cooler than surface conditions, and explosive stability improves dramatically. The excavation proceeds in a brutal rhythm. Drill, blast, clear debris, repeat. Each cavity requires approximately 200 blast holes drilled in a precise geometric pattern that Rigger calculates to fracture the rock in layers from the roof down to the floor. Get the pattern wrong, and the blast energy dissipates uselessly, leaving massive unbroken sections that must be re-drilled and re-blasted. Get it right, and 30 pounds of dynamite can fracture 300 cubic feet of rock into removable chunks. The debris clearing is backbreaking work, shoveling fractured coral into wheelbarrows, hauling it up improvised ramps, dumping it into excavations that become the foundation for surface structures. In the first month, the battalion removes 11,000 cubic yards of material using methods that would have been familiar to Roman engineers 2,000 years earlier: human muscle, simple tools, and relentless labor. Japanese bombers make everything worse. The enemy knows the Americans are building something at Espiritu Santo. They just don't know exactly what or where, so they bomb everything. Raids come at dawn, dusk, and sometimes during the brilliant tropical midday when visual bombing accuracy is highest. The Seabees learn to recognize the sound of approaching aircraft by the change in pitch of their engines, giving them perhaps 90 seconds to take cover. The partially completed underground chambers become life-saving shelters during raids. Men abandon tools and sprint for the excavations, cramming 50 or 60 bodies into spaces designed for fuel tanks, hunching against the coral walls as the island shakes from near-miss explosions. On December 7th, a 500-pound bomb detonates 40 yards from the main excavation. The blast wave funnels down the access tunnel, extinguishing lanterns and filling the chamber with choking coral dust. When the dust clears, every man inside is deaf and disoriented, but alive. The coral roof hasn't even cracked. By January 1943, the Santo fuel dump is operational. 12 buried tanks connected by 2 miles of underground piping feeding a camouflaged pumping station built into the shoreline. From the air, the facility is invisible. The tank vents are disguised as natural coral formations, the access hatches hidden under removable sections of jungle vegetation, and the entire installation covered with sufficient overburden to survive anything short of a direct hit from a 1,000-pound bomb. Cost in American lives, 9 dead, 23 wounded. Cost in time, 87 days, 27 days over the original schedule. Cost in explosives, 6 tons of dynamite. But the result is a fuel depot that will operate continuously for the next 30 months, surviving dozens of bombing raids without sustaining serious damage, providing the aviation gasoline that keeps American bombers flying against Japanese targets throughout the Solomon Islands campaign. The Santo project establishes the template for underground construction across the Pacific, but each new island presents unique geological nightmares. At Funafuti in the Ellis Islands, Navy engineers confront the opposite problem from Espiritu Santo. The entire atoll is made of young, porous coral barely 20 feet thick over a substrate of loose sand and coral rubble. You can't excavate because there's nothing to excavate into. The solution requires importing the ceiling. The 16th Construction Battalion, arriving in August 1943, builds what they call splinter-proof shelters, reinforced structures designed to survive near-miss explosions and the hurricane of shrapnel and debris that accompanies bombing raids. The design is brilliant in its simplicity. Excavate down to the sand layer, build a frame of salvaged steel I-beams and coconut log pilings, roof it with pierced steel planking overlaid with sandbags and coral fill, then bury the entire structure under 6 feet of additional coral. The walls are double-layered, an outer shell of coral block and an inner wall of sandbags filled with local sand, creating an 18-inch barrier that absorbs blast energy without collapsing. The construction technique maximizes use of local materials. Coconut palms, which cover the atoll in profusion, are felled and stripped to create load-bearing posts. Each log is treated with creosote, precious stuff, shipped 8,000 miles from California to prevent termites from reducing it to hollow shells within 6 months. The coral blocks are cast on site using a mixture of crushed coral, sand, Portland cement, and seawater. The recipe violates every construction standard known to American engineering. Saltwater concrete is supposed to crumble within years. But Seabee engineers discover that Pacific coral contains enough calcium carbonate to partially neutralize the corrosive effects of salt, producing blocks that achieve adequate strength for protective barriers even if they won't last decades. The Funafuti shelters are tested under combat conditions on October 4, 1943, when 18 Japanese bombers attack the island's airfield. The raiders drop 72 bombs across the base facilities, cratering the runway and destroying 2 aircraft caught on the ground. But the 140 men inside the splinter-proof shelters survive without casualties. Post-raid inspection reveals that 3 bombs detonated within 30 feet of occupied shelters. The blast effects are dramatic. Coconut logs are shredded by shrapnel, outer coral walls are cracked and partially collapsed, and the steel roofing is dimpled by bomb fragments. But the inner walls hold, the roof stays up, and the men inside report the explosions sounded like distant thunder rather than the apocalyptic roar men experience above ground. The shelters work. Hardened aircraft revetments represent another critical innovation in Pacific underground construction. Traditional airfield doctrine places aircraft in the open or under fabric hangars that offers zero protection against bombing or strafing. This makes every plane a sitting duck. At Guadalcanal, in November 1942, Marine squadrons lose more aircraft to Japanese night bombing raids than to air combat. The solution is the revetment, a 3-sided protective barrier that shields parked aircraft from blast and shrapnel. But building revetments on coral atolls requires excavating defensive positions where no excavation should be possible. The 44th Construction Battalion, working at Tarawa after its capture in November 1943, develops the tractor scraper technique for rapid revetment construction. The method uses bulldozers dragging towed scrapers to excavate coral fill, which is then formed into protective berms shaped like horseshoes open on one end. Each revetment is designed for a single fighter aircraft with walls 10 feet high and 3 feet thick at the base, tapering to 18 inches at the top. The walls are compacted in 6-inch lifts using water and a vibrating roller, creating barriers dense enough to stop 20-millimeter cannon shells and absorb shrapnel from bombs detonating 200 feet away. The work proceeds at shocking speed. A 6-man crew with 2 dozers and a scraper can complete 1 revetment in 6 hours. Within 3 weeks, the battalion constructs 75 revetments at Tarawa's airfield, providing protective parking for every fighter and bomber operating from the island. But the real engineering tour de force occurs on islands with volcanic geology, where American forces can use the terrain itself as protection. At Bora Bora in the Society Islands, Navy engineers confront a different challenge: installing 8 7-inch naval guns on mountainous terrain that provides excellent fields of fire but offers zero level ground for conventional gun emplacements. The solution is to go into the mountain rather than trying to build on it. Starting in March 1942, the 1st Construction Detachment, the original Bobcats, begins cutting gun positions directly into volcanic basalt on slopes exceeding 40 degrees. Each position requires a chamber 30 feet wide, 40 feet deep, and 20 feet high, carved from solid rock, using techniques that combine mining engineering with medieval siege warfare expertise. The excavations begin with hand drilling, teams of men taking turns rotating and striking steel drill rods with 8-pound sledgehammers, creating blast holes 3 feet deep and 2 inches in diameter. In the dense basalt, each hole requires 30 to 40 minutes of continuous hammering. Once a pattern of holes is completed, explosives are loaded and detonated, fracturing the rock into removable pieces. The debris must be hauled out by hand. There's no room for mechanical equipment on the 45-degree slopes, loaded into improvised sleds made from coconut logs and allowed to slide down to collection points where trucks can reach them. It takes 40 men 6 weeks to excavate a single gun position. By September 1942, all 8 positions are complete, virtually invisible from the sea, providing 360-degree coverage of the harbor approaches and capable of surviving direct naval gunfire from anything smaller than battleship-caliber weapons. The Bora Bora positions include an innovation that becomes standard for Pacific fortifications: multiple escape routes. Each gun chamber connects to the surface through 3 separate exits: the main access tunnel, a ventilation shaft that doubles as an emergency escape route, and a concealed third exit hidden in the jungle behind the position. This redundancy saves lives on multiple occasions when bombardment or accident blocks primary exits. The positions also include underground ammunition magazines excavated into the mountain behind the gun chambers, connected by narrow tunnels barely wide enough for 2 men to pass, carrying 70-pound artillery shells. The magazines are double-doored with blast-proof barriers, ensuring that even if the gun position takes a direct hit, the ammunition won't detonate and kill everyone inside. The Typhoon threat requires engineering solutions as challenging as bomb protection. Pacific Typhoons generate sustained winds exceeding 140 miles per hour, with gusts approaching 200. These storms can strip away anything not literally buried or anchored into bedrock. At Guam, where the 38th Construction Battalion begins work in August 1944, following the island's recapture, engineers face the dual challenge of protecting facilities from both Japanese air raids and the annual typhoon season that runs from June through November. The solution combines underground construction with what military engineers call hardened above-ground structures, buildings designed to survive extreme conditions through superior design rather than concealment. The Guam Hospital Complex, designed to treat 3,000 patients, demonstrates this hybrid approach. The critical facilities, operating rooms, intensive care wards, medical supply storage, and the blood bank are built underground in excavations cut into volcanic hillsides. The chambers are roofed with captured Japanese steel I-beams, covered with 3 feet of reinforced concrete, and buried under 6 feet of compacted earth and coral fill. Internal ventilation uses a forced air system driven by diesel-powered blowers in separate underground chambers, ensuring that even if the surface facilities are destroyed, the underground sections can continue operating. The patient wards, which require more space and better natural ventilation than underground construction can provide, are built above ground using a revolutionary design. Semi-cylindrical Quonset huts anchored to concrete foundations with expansion bolts sunk 6 feet into the volcanic rock. The curved profile deflects wind forces rather than resisting them head-on, and the steel construction flexes under extreme loads without failing. The Guam Hospital survives its first major test on November 9, 1944, when Typhoon Ursula hits the island with sustained winds measured at 165 miles per hour. The storm destroys 70% of the island's temporary structures, sinks 2 ships in Apra Harbor, and kills 3 sailors. But the hospital complex survives essentially intact. The underground sections experience 0 damage. The surface Quonset huts lose some exterior panels and suffer bent framing, but remain structurally sound and watertight. Most remarkably, the facility continues operating throughout the storm, with surgical teams performing emergency operations underground while the typhoon rages overhead. Post-storm inspection reveals the critical importance of the deep anchoring system. Huts, anchored with conventional methods, pulled loose and rolled across the island like tumbleweeds, while those bolted to 6-foot-deep foundations stayed put despite forces that would have lifted a conventional building completely off its foundation. The challenge of heat management in underground Pacific facilities requires innovations that wouldn't be out of place in modern climate control engineering. Temperatures inside unventilated underground chambers can reach 120 degrees Fahrenheit, hot enough to cause heat stroke within 30 minutes. Humidity approaches 100%, creating conditions where perspiration cannot evaporate and the human body's cooling system becomes ineffective. Early underground installations at Guadalcanal experience casualty rates from heat exhaustion that approach combat losses, forcing immediate redesign of ventilation systems. The solution, developed by Navy Civil Engineer Corps officers, combines passive cooling with forced ventilation in ways that maximize efficiency while minimizing power consumption. Critical because every gallon of diesel fuel used for ventilation blowers is 1 gallon not available for vehicles or generators. Underground facilities are oriented whenever possible to create natural airflow through the tunnel effect. Position openings at different elevations, so hot air rises and exits through upper vents, while cooler air is drawn in at lower levels. For installations where natural ventilation is insufficient, engineers design ventilation systems using salvaged aircraft blowers, powerful, reliable, and designed to operate in extreme conditions. A typical underground fuel storage complex at WWII employs 6 blowers in series, each positioned in a side chamber so that mechanical failure or battle damage to one doesn't shut down the entire system. The cooling effect is enhanced by the thermal mass of the surrounding rock. Volcanic basalt and dense coral maintain relatively constant temperatures 12 to 15 degrees cooler than surface conditions. By continuously circulating air through the chambers and allowing it to contact the rock surfaces, engineers achieve meaningful cooling without refrigeration equipment. The system isn't perfect. Underground working conditions remain brutally hot by any standard, but temperatures stay below 95 degrees even when surface conditions exceed 110, and humidity drops enough that perspiration can evaporate, allowing human bodies to cool themselves through natural mechanisms. One of the least known but most critical underground construction projects occurs at Tinian in the Marianas, where the 6th Construction Battalion builds the atomic bomb assembly facilities in absolute secrecy during June and July 1945. The specifications are unprecedented, create a climate-controlled underground workshop capable of assembling the most complex weapon ever built, with ventilation systems that maintain humidity below 50% and temperature below 75 degrees, all while providing complete concealment from Japanese reconnaissance aircraft still operating from nearby islands. The facility must also survive near-miss explosions from the 500-pound bombs Japanese raiders occasionally drop on Tinian's airfields. The construction crew receives no information about what the facility will house. They're told only that it requires extraordinary environmental controls and security. The excavation, cut into a hillside near the Northfield bomber runways, creates a main chamber 60 feet long, 40 feet wide, and 15 feet high, with 3 smaller adjacent rooms for storage and support equipment. The climate control system is the most sophisticated installed anywhere in the Pacific. Diesel-powered refrigeration units cooled by seawater pumped from the coast 3 miles away, air circulation through fabric ducting that distributes cooled air evenly throughout the chamber, and dehumidification equipment operating continuously to remove moisture from the tropical air. The electrical system includes redundant diesel generators in separate underground chambers, ensuring that power failure cannot compromise the facility. The walls are lined with salvaged plywood to create an interior vapor barrier, reducing condensation that would otherwise rain from the rock ceiling onto anything stored inside. The floor is poured concrete, precisely leveled and sealed to prevent dust contamination, a requirement the construction crew finds baffling until they learn, months later, that they've built the facility where the Hiroshima and Nagasaki bombs were assembled and loaded onto their delivery aircraft. The facility's existence isn't declassified until 1960, and by then the underground chamber has been abandoned and partially collapsed. its contribution to ending the war forgotten by everyone except the 220 Seabees who built it. By war's end, American forces have constructed more than 1,500 underground or hardened facilities across the Pacific, ranging from simple bomb shelters protecting a dozen men to massive tunnel complexes housing entire headquarters staffs. The casualties among construction personnel are sobering. 342 Navy Seabees and Army engineers die in construction accidents or enemy action while building these facilities. But the lives saved number in the tens of thousands. At Iwo Jima, underground command centers allow American forces to coordinate artillery and air support throughout the battle while Japanese bombardment craters the island's surface. At Okinawa, underground hospitals treat 12,000 wounded Americans in facilities that survive kamikaze attacks, naval bombardment, and artillery barrages that would have annihilated surface medical stations. The technical lessons learned in Pacific underground construction influence American military engineering for decades. The shaped charge protection techniques developed for ammunition bunkers at Guam become standard for Cold War nuclear weapons storage facilities. The forced ventilation systems designed for tropical underground chambers evolve into climate control systems for missile silos and command centers. The rapid excavation methods using commercial explosives and hand tools, refined on coral atolls under combat conditions, are still taught at military engineering schools as solutions for situations where heavy equipment is unavailable or impractical. But perhaps the most important legacy is psychological, the demonstration that American ingenuity and industrial capacity can overcome any obstacle, no matter how hostile the environment or desperate the circumstances. The engineers who carved gun positions from volcanic mountains, who buried fuel tanks under coral atolls, who built operating rooms into hillsides while Japanese bombers hunted them from above, these men proved that American forces could not just survive in the Pacific, but thrive, turning every captured island into an unsinkable aircraft carrier, every atoll into a fortress, every reef into a supply depot. The Japanese had assumed that logistical difficulty would stop American expansion across the Pacific. Instead, American engineers used the Pacific itself as a weapon, burrowing into its islands, hardening its beaches, and transforming its geography into the foundation of victory. The numbers tell the story of industrial warfare at its most fundamental level. Between 1942 and 1945, Navy construction battalions excavate over 12 million cubic yards of material across Pacific Islands, enough to fill the Empire State Building 4 times over. They pour 6 million cubic yards of concrete, much of it reinforced and much of it used for underground structures. They install 78,000 tons of structural steel, assemble 42,000 Quonset huts, and build 3,500 miles of roads connecting facilities scattered across archipelagos spanning half an ocean. They accomplish this while under air attack, while suffering from tropical diseases that hospitalize 30% of personnel at any given time, while working with tools and equipment that corrode and fail in the hostile climate, and while operating 8,000 miles from the nearest American factory. The Japanese never developed comparable construction capabilities. Their fortifications, while often ingenious and certainly deadly to attacking American forces, are essentially defensive positions rather than operational bases. They lack the logistical infrastructure, the construction equipment, and the engineering expertise to match American underground construction. More critically, they lack the industrial capacity to replace what they build. When American forces destroy a Japanese underground position at Peleliu or Iwo Jima, it cannot be replaced. When American forces lose an underground facility to bombing or shelling, construction battalions rebuild it within days using prefabricated components and standardized designs. This asymmetry in construction capability becomes a strategic weapon as important as any bomber or battleship. Every underground fuel depot means American aircraft fly one more mission. Every hardened ammunition bunker means artillery can sustain one more barrage. Every bomb shelter means trained personnel survive to fight another day. The Pacific War is ultimately decided by industrial capacity and logistical superiority, and underground construction is where that superiority becomes most visible. American engineers literally digging victory out of hostile islands, one blast hole at a time, while Japanese forces watch their positions get bypassed, isolated, and eventually starved into irrelevance. The men who built these installations receive little recognition during the war and less afterward. Their work lacks the obvious drama of combat, the clear victories of air-to-air engagements or amphibious assaults. But every pilot who survived a bombing raid in an underground shelter, every wounded Marine treated in a bomb-proof hospital, every ship refueled from a concealed depot owed his life to engineers who fought their war against geology and climate rather than enemy soldiers. They proved that in modern industrial warfare, the ability to build determines who wins just as surely as the ability to fight. And they demonstrated that American engineering ingenuity, backed by industrial resources and driven by desperate necessity, can accomplish feats that seem impossible until they're done. Then they just become the new standard for what engineering can achieve under the worst conditions imaginable.